In Part 3 of Lecture 3, we take a look at an example of a symbol table manager. After the scanner assembles the lexeme, it must determine if it is already in the symbol table. If so, and it is either declared as a global or within the current scope, its token is already determined. If the lexeme is not already in the symbol table, then it must be installed and assigned a token, either as a literal or as an identifier. This also requires that we create an entry in the attribute table. If the lexeme is an identifier and already in the symbol table, but does not belong to the current scope, a new scope must be opened for it. The method installName returns true if the lexeme is already in the symbol table and has an entry in the attribute table. If it is in the name table but there is no attribute table entry, we will create one and return false. If the lexeme is not in the symbol table, we need to copy the string into the string table and to create a name table entry. We will also need an entry in the hash table so we can search for it and find it. And we need an attribute table entry so we will be able to store information about it. And we need to return false. This will allow us to add the basic information to the attribute table entry for the symbol. Is present determines whether the symbol in question is in the symbol table. Old name index will keep track of the previous index in the name table. We will need it later, but it is initially -1 because we have not yet found the name table entry. The next task is to find the hash value for the lexeme. We will start our search for the name table entry at the index indicated in the hash table. If this entry is not the string that we seek, we will go to the next entry with the same hash value. We will continue this until we have either found the lexeme's entry in the name table, or we get an index of -1, meaning that there are no more entries with this hash value. Once the lexeme is installed in the symbol table, an entry must be created for it in the attribute table. The function installAttrib will create the entry, initialize a pointer back to the name table, set the semantic type and the data type both as unknown. The function setAttrib will set the semantic type, the token, and the data type, as well as link the entry to any others for that scope. Here we see the method installAttrib. We first get the index for the new entry. We save the index of its name table entry and set semantic type and data type as we said before. The method setAttrib sets the values for certain attributes, namely the semantic type and the token, and it will set the data type to either none or unknown. Reserved words and operators have no data type, but literals and identifiers do. However, we will set the data type a little later during semantic analysis. Additionally, if this lexeme is an identifier, we will need to include it in the current scope. If we don't already have a linked list of variables declared within this scope, we will start one. Otherwise, we will add it to the list. Installing data type is done by the semantic analyzer during the processing of declarations. Until this point, identifiers have their data type listed as unknown. The same function, installDataType, installs the correct semantic type as well as the correct data type. Block-structured languages such as ALGOL, PL1, Pascal, C, C++, and Java have to allow for the fact that the same identifier may mean completely different things in different scopes. Strictly speaking, a block is a program structure in which there can be declarations. For example, although it is unusual to place declarations in C blocks, excluding the main block of a function, it is perfectly legal. Because such languages resolve name conflicts using a most closely nested scope rule, languages with static scoping rules must have a mechanism for temporarily hiding a variable in an outer scope. In implementing a symbol table, this means either separate symbol tables for each scope, or identifying the scope to which each identifier belongs. Keeping track of a scope requires two different linked lists. One that we will create links the identifiers together that belong within a given scope, from the first one declared within the scope through the last one. This will simplify the process of closing the scope when we are finished. We also keep a linked list of identifiers sharing the same name, pointing from the most closely nested scope outward. The beginning of the list is the version of this identifier most recently declared in the innermost scope that is still open, going back to the oldest version declared in the outermost scope that is still open. Additionally, each identifier is marked with a pointer to the symbol table entry of the procedure which owns this version of the identifier. Opening a new scope involves creating a new entry in the attribute table, readjusting the name table pointer to point to the new entry, and vice versa, linking the new entry to the other entries in the new scope, as well as to the other older entries sharing its name. Closing the scope will involve readjusting the pointer in the name table to point to the next scope outwards for that identifier, and possibly writing the data on disk and clearing the entry, as done in some circumstances. Identifiers declared in a new scope are added to this new scope, one identifier at a time. The one parameter of the OpenScope method is the index in the attribute table, and this is used to get the index in the name table. A new attribute table entry is necessary for this new scope, and its semantic type is set as unknown, and the token as identifier. The outer scope is set as the attribute table index of the previous scope, so it can be restored as the current scope when the compiler leaves this one. When we leave this particular block, its scope is closed, and all the identifiers declared in it are hidden from view. The entries are still available to the methods that need them, because they have access to the attribute table index. We'll look at the start of the scopes list, and each identifier has its name table entry point back once again to the previous scope. There are a variety of miscellaneous methods, most of which are accessors and mutators, to give other phases of the compiler access to the data within the symbol table. getToke class returns the token for a given symbol. setproc sets and changes the owning procedure for a given symbol, and getProc provides the reference to the methods that need it. Both setValue methods will set the value of a literal in the program. It is important to know that both the tag and the value must be set. The tag allows the value to be either integer or real. If you look at the two versions of it you see on the slide, the first one assumes that the value is real, and the second one assumes that it is integer. Print lexeme allows the compiler to print out the lexeme. This is helpful both when the compiler is being debugged, and it also allows an error message to include the name of the variable involved in the compile time error. Print token allows the token to be printed when debugging the compiler. Since algol-based languages can have procedures embedded in procedures, it is often necessary to have a stack to handle the various scopes that we can have within the program.